Hello, in this video I'm going to present statically verified refinements for multi-party protocols. So let me begin with explaining the title. So what are the multi-party protocols that we are talking about? In message passing concurrency, an important typing discipline is the multi-party session type. In this methodology, a global type describes the communication behavior of all participants in the multi-party protocol. A local session type, also known as a local type, describes how a single participant interacts with other participants in this global picture, and it can be obtained via an operation called projection from the global type. The local types can then be used to guide the implementation of endpoints, for example by code generation or type checking. After all, the endpoint processes are free from deadlocks or communication mismatches. For example, let's consider this game between three participants. It is a guessing game where A tells B a secret number and C can make a number of guesses to B. After each guess, B will respond either with higher or lower, indicating C should change the guess, and C can subsequently make another guess, or when the guess is correct, the game will end. We can formalize this protocol with the global type on the right hand side. So first of all, there is a message from A to B with label secret carrying an integer. This is followed by a recursion beginning with a message from C to B with label guess and an integer, and subsequently B will send to C three options: higher, lower, or correct. In the case of higher and lower, the protocol continues with recursion. In the case of correct, the protocol terminates. If we focus on the communication behavior of the participant C as highlighted in the sequence diagram, we obtain the projection of the global type upon the participant C. Notice that the first message in the global type is from A to B, not involving the participant C, which we are currently focusing on. Therefore, in the projection, the first action will be an internal choice to send to B, and subsequently followed by an external choice from participant B. While the multi-party session type is able to guarantee that there is no deadlock or communication mismatches, so we know that we will receive an integer when we expect an integer instead of other payload type, for example strings. However, for this particular example, there are other properties we are interested in. For example, whether the higher, lower, or correct cases are entered only when they should be entered, namely according to whether the secret is greater than, less than, or equal to the number guessed. And this leads to the second part of the title, refinements. In the typing discipline of refinement types, base types can be refined with predicates in a set-like notation as shown in the slides. For example, natural numbers are integers that are greater or equal to 0. By integrating multi-party session types and refinement types, we gain more expressiveness on the data aspects. And last but not the least, statically verified in the title means we produce a toolchain for implementing multi-party protocols with static verification. For these purposes, we target our toolchain to the F-star programming language, which has support for refinement and dependent types. In particular, the refinement type implementation in F-star is assisted with an SMT solver Z3 that supports automated verification. After type checking, the verified code can be extracted to OCaml for efficient execution. In our paper, we present a theory combining the multi-party session type and refinement types, allowing more expressive protocols to be specified, and also a toolchain implementation for implementing refined multi-party protocols. Our paper is also accompanied with an artifact that is available, reusable, and functional. And I will first begin with the theory. We go back to the number guessing game example that I described earlier, where we use this global type to describe the communication protocol. As I mentioned, we would like to ensure that higher, lower, and correct branches are only entered where they are supposed to be entered. Suppose we call the secret S and the guess G, and the higher branch indicating the next guess should be higher should only be entered when G is less than S. And we see that the updated global type is now refined with refinement types. So we require that the higher branch is only entered when G is less than S, and we use a refinement type for that. And for simplicity, we omit the payload type of higher, lower, and correct, which are all units. However, an important thing to notice is that the secret is only known between the participant A and B. So when we project this protocol into the participant C, the message A to B with label secret and payload S will disappear. If we extend the definition of projection naively, we will end up having unbound variable S in the projected local type. Whereas the exact value of the secret S is known to the participant C, they may still salvage some information from its type. For example, if the type of the secret S is integers that are between 0 and 10 inclusive, and C makes a guess 9 and got a response that says higher, although the explicit value is not communicated to C, C can conclude that it must be the case that the secret is 10. In our theory, we use typing context to track the knowledge of variables. So when two participants exchange a message, the value of the variable will be known to only these two participants, where all the other participants knows that this exchange has occurred, but only the type information is available. And we need to distinguish whether a participant actually knows the value of the variable. At the global type level, we use a set of participant big P to denote the set of participants who know the value of the variable. At the local level, we annotate a variable with a multiplicity that we can choose between 0 or omega. 0 indicates that the variable is irrelevant, so only the type information can be used, not its actual value, and omega indicates both the type and its actual value are known. Since we have a refinement type system, despite the value not being known, its type information can still be helpful when proving properties. For a more concrete example, if A sends B a variable x, this variable will be known to A and B, and these will be unrestricted, carrying multiplicity omega for A and B. And in the local typing context of C, C knows the existence of the exchange, but its value is unknown, hence the multiplicity carried by X is 0. We also give semantics to our refined multi-party session type using labeled transition systems. The global types are given a label transition system for their semantics, as well as local types. The important result of the multi-party session type methodology is that projection preserves traces. If the global type transitions from G to G prime, the system of local types projected from G and G prime should also make the same move alpha in the transition system. This is known as the trace equivalence theorem. We also proved the trace equivalence theorem for the new theory of refined multi-party session type. We include the typing context in the labeled transition system to model the evolving knowledge as the protocol progresses. For details of the syntax and semantics of the global and local types, please have a look at our paper. For the second part, I'm going to introduce the toolchain for implementing refined multi-party protocols. We present the workflow of our toolchain, session star, in this slide. The development process begins with a protocol description in Scribble, a multi-party protocol description language. Then, a code generator generates F-star APIs and types from the Scribble protocol after validating the protocol. Developers then implement these APIs using the generated types in F-star, and the F-star compiler will type check whether the implementation satisfies the refinement typed APIs. If the program succeeds in type checking, the compiler can then extract the verified programs into OCaml code for efficient execution. Our artifact is available as a Docker image, and the source code can be found in the GitHub link. So, let's begin with specifying a protocol in Scribble. We come back to our example of the number guessing game and try to specify the protocol in Scribble. Scribble by itself provides a nice syntax for developers to specify multi-party protocols, and our toolchain uses an extended version of Scribble that allows refinements. Refinements can be attached as annotations after the @ symbol. The next step is to generate the APIs and types from the protocol in F*. Traditionally, APIs for session types look a bit like this. First of all, you establish a connection using the connect primitive, and it returns a session. Further operations on that communication channel will happen on that session. For example, the receiveSecret function takes in a session and returns a session that is used for the continuation of the protocol and the secret value. After a number of operations, all the operations are completed and the session can be closed with close primitive. It is very crucial that the session channel S is used and only used once. This is known as the linearity requirement. Having a session channel used multiple times leads to communication errors, and so as dropping a channel silently. The linearity of communication channels are either enforced by a linear type system or dynamic checks that occur at runtime. In our work, we introduce a new callback style API that guarantees linearity by construction. This is done by generating a number of type signatures for callback functions and requiring developers to implement these callbacks. The callbacks will be executed by the runtime and dispatched according to the progression of the protocol. For instance, for the internal choice of B to decide between sending correct, higher, or lower, we generate this choice send type where a state is provided and a choice is expected. The refinement types ensure that the choice is only entered when the side conditions are satisfied. On the receiving side, upon the receipt of the message, the corresponding callback will be fired and the user can do some processing when the callback is fired. For instance, an implementation may use a binary search algorithm and the higher and lower bounds can be updated on receiving a higher or lower message. Although the participant C does not know the value of the secret S, we still retain the refinements regarding the variable S. However, the variable st.s carries an erase type so that it may only appear on the type level. The next step is for the developers to implement the endpoints according to the generated types. Let's have a look at how B decides whether to send correct, higher, or lower after receiving the secret number and the guess. The type requires that the send handler to be a function that takes a state and returns a choice. So an implementation would take the state as an argument and compare the guess and the secret that are inside the state. If the guess equals to the secret, then return correct as the choice. Otherwise, if G is less than S, the guess needs to be higher, so we send higher. Otherwise, we send lower. If a programmer makes a careless mistake, for instance by flipping the sign of the comparison, the condition inside the type will not be satisfied and these errors can be detected by the F* type system statically. Overall, we rely on the refinement type system of F* to help us validate all the refinements in the multi-party protocol. For a full walkthrough of the higher-lower example, please have a look at our paper and accompanying artifact. For future work, we would like to study how to mix verified and non-verified participants. We acknowledge that refinement types are not yet that prevalent in mainstream programming languages, especially in distributed computing, and we can use other means, for example a monitor, to achieve similar goals. On another side, we would also like to look for ways to improve the expressiveness of the toolchain, for example using custom specified predicates. Thank you for your attention and I look forward to your questions in the Q&A.